Okay, hi guys. It is a beautiful Friday morning and this is our last day before phase 2 begins. So I thought I would do a unit 2 chemical reactions review. So this is everything that you need to know from our unit review for unit 2. Now, remember, we haven't had any quizzes, we haven't had any tests from this unit, so I don't know where you guys are at. So you can expect either an assignment, a quiz, a test, an online something. So you need to know this information, but you also need to know it for the rest of chemistry. So the first one that we're going to talk about are synthesis and decomposition reactions. All right, so the first one that we're going to look at are simple binary, so that means 2 compounds. Just move this. So for an example of this one, we are going to have sodium solid combining with chlorine gas. So chlorine is Hofbrinkel. So remember, all of these ones, they come as diatomic. All right. So when I'm balancing out sodium and chloride, I'm going to crisscross and see that, okay, it's just going to be NaCl aqueous. And to balance it out, I need 2 and I need 2. So that is just a simple synthesis reaction. And then let's see if we have just another simple decomposition reaction. I'm going to have barium. Barium is a solid, I see off of the periodic table. And then I have fluorine. Fluorine is a gas. So again, where I'm getting solid, gas, aqueous. This one, I know that I'm making it in an aqueous solution, but everything else I'm getting off of the periodic table. Okay. So moving on, let's talk about the more complicated ones. So I have metal chlorides plus oxygen. So let's think about, I have calcium chloride, and so this is going to be solid, it's an ionic compound, plus oxygen. So our rule is that metal chlorides and oxygen, they're going to form a chlorate. So off of the periodic table, or sorry, off of your polyatomic ion sheet, I know that chloride is ClO3. It has a charge of -1, and I have to crisscross it with calcium chloride. So I'm going to have calcium, crisscross it with calcium. I'm going to have calcium chlorate. This is going to be aqueous. All right, let me just erase this part down here. So looking at it, now I have to balance it. So calciums are balanced, chlorides are balanced, but now oxygen, I have 6 oxygen, so the way I'm going to balance it is 3 over here. And so just like a decomposition reaction, say if I have sodium chlorate, again, it's going to be a solid. When it decomposes, it's going to be sodium chloride plus oxygen gas. And so to balance that, I need 2 and 2 and 3 here. Okay, so that's one of our synthesis and decomposition reactions. The next one I want to talk about are metal oxides plus carbon dioxide. And I'm sorry how terrible my writing is. Okay, so let's think about, we have a metal oxide. Let's do magnesium oxide. So this is going to be a solid. What's going to happen with carbon dioxide gas? So you have to think about what polyatomic ion it's going to form, and it's actually going to form a carbonate. So carbonate is 2-, and we're going to balance it with magnesium, which is a 2+ ion. So when they balance out together, we're going to have a 1-to-1 ratio, and so it's going to be magnesium carbonate, and that will be a solid. Or it could be aqueous, I'm not too sure. Probably aqueous, but it doesn't matter for that one. All right, so metal oxides plus carbon dioxide, they form metal carbonates. Our next one that we're going to talk about, these are the two important ones for acid and base synthesis. So if I have a metal oxide plus water, is it going to be acid or base synthesis? So I'm going to take calcium oxide, solid, plus water, liquid. Think about what's going to happen. So calcium is a 2+ ion. Is it going to form an acid and crisscross with hydrogen, which is another cation? No, it's going to crisscross with hydroxide, which is an anion. And this is going to form calcium hydroxide. And that's going to be aqueous. Okay, so this is base synthesis. Okay, and if you remember from class, a non-metal oxide plus water, well, if a metal oxide plus water forms bases, then a non-metal oxide plus water is going to form acids, okay? So for instance, if we have SO3 aqueous plus H2O liquid, it's going to form H2SO4, which is sulfuric acid, right? And these ones, because they are more complicated, and it requires you looking at oxidation numbers to be able to balance them, we're skipping over that. Okay, so now let's move on. Those are all the different types of synthesis and decomposition reactions. I only showed the synthesis reactions because just reverse the equation. So instead of having a forward arrow, if you have, think about sulfuric acid breaking down to water and sulfur trioxide, that's going to be the decomposition reaction. So I'm not going to go through each one of them there. Let's move on to single displacement reactions. So this is, there's two different types. And the first one that I'm going to look at are cations displacing cations. So mostly it's metals displacing metals. The first one, the first example of this is just simple metal displacement. All right. So let me just change the, oh, what did I do? Okay, so I'm just going to change into this, change the color. So simple metal displacement, we have to look on the activity series, okay? So an example of this is if I'm looking at gold chloride, so this is going to be an aqueous compound, it's dissolved in water, and if it's reacting with magnesium solid, if you look on the reactivity series, you're going to see that gold is all the way at the bottom. Magnesium is going to be able to give its electrons to gold, and it's going to form magnesium chloride, and it's going to displace gold and make it into a solid precipitate. And then you're just going to balance it out. Okay, so I can do these in my head. I'm able to think, okay, magnesium is a 2 plus charge, chlorine is a 1 minus charge. So when I crisscross, it's MgCl2. So make sure that you show your work, make sure that you're checking how everything is balancing out. Now, because there are going to be more reactive and less reactive metals, we sometimes have reactions that do not proceed. So an example of this is I'm going to take lithium fluoride. Oh dear, I don't like that crayon at all. I'm going to take lithium fluoride, aqueous, plus aluminum, solid. Lithium is much, much more reactive than aluminum. And so we can predict, we can say that, yeah, it's going to form, it could form aluminum fluoride plus lithium solid. No, actually it's not, okay? So because lithium is higher on the reactivity series than aluminum, aluminum is not able to displace it in an ionic compound. But you see, I still predicted what would the possible products be, and then I'm going to write underneath no reaction. Okay, so that is for simple metal displacement. We can also have metals displacing hydrogen in acids. So if you remember the reactivity series that I gave you, there's 3 different arrows. One is just the reactivity series. The other one is displaces hydrogen in acids. So let's look at an example of a reaction that proceeds. I have hydrochloric acid plus potassium metal. So potassium is a very, very reactive metal. It is within that arrow, it is higher than hydrogen. It is able to kick out hydrogen. So because it's going to kick out hydrogen, it's going to react with chlorine. So potassium is +1, chlorine is -1. We're going to have potassium chloride aqueous, plus hydrogens always come in pairs. They're diatomic. So we're going to have hydrogen gas. We have to balance it out. Okay, and this is what a displacement reaction will look like that displaces hydrogen from acids. Let's look at an example of one that isn't able to do it. So I'm going to still work with hydrochloric acid, but let's take something that we wear, silver. There's a reason why we wear silver, there's a reason why we wear gold. It's because it's all the way at the bottom of the reactivity series. It doesn't react with much. So we're going to predict what is it going to look like. Well, silver chloride should be produced, as well as hydrogen gas, and then, okay, I can balance it out, whatever. But guess what? It does not react. So I can make the predictions. You don't really have to balance it out if it doesn't react. And then underneath, I'm going to say no reaction. Okay? And the reason why is, look on your reactivity series. Silver does not fall within that arrow of being able to displace hydrogen from acids. It's all the way at the bottom, meaning that it does not have the reactivity to be able to displace hydrogen. Okay, and now for the one that students notoriously forget, which is metal displacing hydrogen in water. Okay, so I'm going to pick a very reactive metal. I'm going to pick lithium. And then I'm going to, so this is lithium solid. Now, I'm going to draw water molecules. Doesn't it feel like so long? I was forcing you guys to draw dipoles and things like that. And we're going to break apart the water molecule. We're going to analyze it. And if you look at it, this is the one bond that can be broken. Okay, well, there's 2 of them, but it's more difficult. Chemistry, you start with step by step. So this is the hydroxide ion part. This is the hydrogen ion part. So when I'm looking at what's going to happen, lithium is going to be a positive cation ion, and it has the choice to either react with the hydrogen, which is H+, or the hydroxide ion, which is OH-. Well, the law of electric charges says this is not going to happen. It's going to repel each other, plus and plus, whereas plus and minus, they love each other, okay? The law of electric charges, opposites attract. So we're gonna have lithium hydroxide form, and that's an aqueous solution, or that's an aqueous product. What is the byproduct? Hydrogen, H+. This hydrogen does not like to stay by itself, so it's gonna form H2 gas. If you were there when I did my demonstration, you would have seen that we had when I put potassium in water, we had a flame, and we had some reactivity with the hydrogen gas. Okay, so now I still have to balance it. I'm gonna have 2 of these, I'm gonna have 2 of these, and I'm gonna have 2 of these. What would a reaction, what would something that's not able to displace water? Well, the first one I believe on, oh gosh, I did it again. The first the first metal that isn't able to do it, I believe is aluminum. I don't have it in front of me, but it's just not reactive enough. So you aren't going to have aluminum hydroxide form, okay? It's not able to do that reaction, and so it's not able to form a hydroxide. All right, so that is single displacement of cations taken care of. Well, we can't forget our anions. So single displacement. So the only anions that are able to replace each other are halogens. So it's halogen displacement. What is our reactivity series for halogens? It's the periodic table. So remember, you'll always have the periodic table in front of you. It seems like for the rest of the semester, you'll have your textbook and internet in front of you too. So hopefully you won't have any confusion. All right, so we start, the most reactive halogen is fluorine, then comes chlorine, then comes bromine, then comes iodine, okay? So this is the most reactive, this is the least reactive. So when I'm doing an example of a reaction that does proceed, I have salt. I'm going to bubble into that solution fluorine gas. Well, fluorine is higher than chlorine, and so it's able to steal the electrons from chlorine, and you're going to get sodium fluoride plus chlorine gas formed. And then again, we have to balance it out. Right, what would an example of a reaction that does not proceed look like? Let's take calcium bromide, or no, let's take calcium chloride, aqueous, and try to react it with bromine gas. Bromine is down here and it's trying to punch up, okay? It's trying to go above, it's trying to go higher. It can't, right? In this case, we had fluorine and it's moving down, okay? Bromine is trying to move up. That is not possible. There's no reaction, okay? I guess you could predict what would it be? It would be calcium bromide plus chloride gas. No, not gonna happen, okay? So bromine does not have the ability to displace out chlorine from the ionic compound. Okay, moving on. This is going to be a long video, guys. I'm sorry. I hope you're hanging in there. Okay, so this one, now we're moving on to double displacement. I spelled it wrong. Oh God. Whatever. Double displacement reactions. And this is the one that we're using our solubility guidelines. Okay, so I can't display this on the screen. I'm sorry, guys, but you can have it in front of you. This one I always think of production of solid, production of liquid, production of gas. So the first one I'm going to look at is the production of a solid. And so we call this solid precipitate. So precipitate formation. So let's do an example of a reaction that proceeds. I have silver nitrate reacting with sodium chloride. So when I look at these, I always switch my cations. Okay? So over on this side, I'm going to think now I have sodium reacting with nitrate. It's a 1-to-1. So just NaNO3, okay, plus, now I have silver, which is +1, plus chloride, which is -1. It's a 1-to-1. So I have silver chloride. Look on your solubility guidelines. You'll see that nitrate's rule is that everything is soluble. So I'm going to put aqueous. For chloride, for the halogens, I forget which rule it is. It's most are soluble except for silver, mercury 2, and lead. So this is going to be solid. So this is my solid precipitate formed, which means that this reaction proceeds. Let's look at a reaction that won't proceed. Sodium chloride plus potassium fluoride. Oh, I forgot to change it to blue. Oh, well, whatever. And so again, we're going to switch the cations. So now I'm going to have potassium with chloride, potassium chloride, 1-to-1. And I'm going to have sodium fluoride. Again, it's a 1-to-1. If you look at these are both halogens, so chloride ion and fluoride ion. You always look at the anions, and they're both aqueous. Aqueous and aqueous. So guess what? Nothing occurs. There's no solid precipitate form. There's nothing that, there's no chemical change. There's mixing, but there's no reaction here. All right, so that takes care of solid being formed. Let's look at the production of a liquid. This is going to be neutralization. So you're always going to have to see an acid and a base being reacting. So HCl, aqueous. What makes this an acid? This hydrogen. Plus NaOH, aqueous. What makes this a base? The hydroxide ions. So whenever you have an acid and a base reacting, you're going to have the production of liquid water, which is what we want to see, and then the cation and the anion are going to react with each other. So in this case, we have sodium and chloride. It's going to be a 1-to-1 reaction, so you're going to have sodium chloride aqueous formed. You could also have a solid being formed here, like a solid precipitate. So for example, we have H2SO4 aqueous, this is sulfuric acid, plus potassium hydroxide aqueous. We know that it's going to form water. What's the second one it's going to form? Well, we have the potassium ion and the sulfate ion, and now we're dealing with K2SO4. This is still going to be aqueous, but now we're going to have to balance it out. So basically, I need 2 potassium hydroxides, and I'm going to form 2 waters. This is an acid that has more than 1 hydrogen, which is totally possible, and you just have to balance your reactions based off of that. Our final type of reaction in double displacement is the production of well, we had solid, we had liquid, now we have gas. And that's going to come from the further decomposition of NH4OH, sulfurous acid, H2SO3, and carbonic acid, H2CO3. So let's do an example of each one. So the first one, if I have NaOH aqueous reacting with NH4Cl, when they have a double displacement reaction, I'm going to have NH4OH and sodium chloride being formed. So you have to be able to look at this and say, hey, I have this one formed. So you can just do another arrow underneath and show that NH3 gas plus H2O liquid is formed. Okay, so NH3 is always going to be gas. There's always, whenever these 3 decompose, you're always going to have a gas being formed. Okay, on to the next one. If I have calcium sulfite plus hydrosulfuric acid, when I crisscross them, I have sulfurous acid being formed, and I have calcium sulfide. And this is actually, when you look on your solubility guidelines, it is a solid precipitate. Now I do this really quickly. You should be, looking at calcium 2+, crisscrossing it and reducing it. Okay, but I'm quick with these ones. Take your time. I should always see scribble notes on the side where you're crisscrossing and you're finding out what the ionic compound, the ionic formula is going to be. All right, so again, we have the production of sulfurous acid being here. So what's it going to break down? You're always going to have H2O formed. So if you subtract H2O from H2SO3, what are you left with? SO2, sulfur dioxide gas. And you're still going to have your calcium sulfide being formed here. And then our third and final one is with carbonic acid. So this is the demonstration that I did in class. So calcium carbonate, which is chalk, so it's a solid. And I mixed it with acetic acid, 2,2. Now this one confuses students because do you see how the H is at the end. This is composed of the acetate ion and the hydrogen ion. So whenever you see choo-choo, okay, so that's how I lovingly refer to acetic acid, make sure that you see SCH3CO, O minus, and then an H plus. Okay, so that's how it is made to be an acid. When it crisscrosses, we're going to have calcium pairing up with the acetate ion, and we're going to have carbonate pairing up with the hydrogen ion. So we're going to have calcium, carbonate, and I need 2 of these, and this is going to be aqueous, plus carbonic acid. So I need 2 of those there. We have over here carbonic acid being formed, and it breaks down. So, oops. So we have calcium acetate still being formed, plus, all right, we're going to have water being formed, and then you subtract water from carbonic acid. So H2CO3, you take away the hydrogen, so there's nothing left. You still have the carbon, and you have carbon dioxide, which is going to be a gas. So this, you have either carbon dioxide gas being formed, sulfur dioxide gas being formed, or ammonia gas being formed. Now on to our last reaction type, which are combustion reactions. So we have complete combustion. So this is with an excess of oxygen. This is what we always want to strive for, is to have as oxygen be plentiful, because then you have very clean burning. You've seen it, where there's a truck that's seen better days on the road and should be taken off because what's happening, you have a lot of black soot coming from the exhaust. Clean burning, there is nothing coming from the exhaust. It's much more complicated than that, but that's for another course. All right, so in this case, we're always going to be dealing with hydrocarbons. Why are they called hydrocarbons? Carbon plus hydrogen. We're combining it with the oxygen. The only 2 products you're going to have are carbon dioxide gas plus water vapor. Okay? You balance it out. So the carbons, there's 1 carbon here, 1 carbon here. Great. There's 2 hydrogens here. There's 4 here. So I'm going to put a coefficient for hydrogen for water. Then you're going to balance your oxygens last. On this side, we have 4 oxygens, so I need 2 total here. And you're done. I find these ones pretty easy. Now there's some hydrocarbons that have some extra oxygen, right? So you're still going to deal with it. Oh, I forgot to put gas over here. So you're still just going to put carbon dioxide gas plus water vapor. And when you're balancing it, I have 2 carbons here, so I'm going to put 2. I have 6 hydrogens, so I'm going to put 3. In total, I have 4 plus 3 oxygen, so I have 7 oxygen total. Here I need 7, but guess what? I have this oxygen here. So I only need 6. So my coefficient is 3. In combustion reactions, you are allowed to have fractional amount of oxygens being produced. So say if you were only supposed to have, say if you were to have 7 oxygen, you can just put 7 over 2 O2, and that is an acceptable answer. Okay? But this one, We don't need to do that. All right, and then our last and final one, oh, we made it, guys, is incomplete combustion. This is what's going on when you have that dirty, you have unclean burning. So this is limited oxygen. This is not clean burning. It's inefficient. All right, so for the purposes of this course, we're never going to make you balance it. So I'm just putting X and Y because yay, algebra. And you're going to have the production of carbon dioxide. You're going to have the production of water. But then you have these two. You have carbon monoxide and carbon soot. So CO, this is carbon monoxide. And this is the silent killer, right? It binds to hemoglobin. And it will slowly cause you to suffocate. You're still breathing, but because your red blood cells cannot transport oxygen, because the carbon monoxide has bound to the heme protein, it has a higher affinity to the heme protein than oxygen. Your blood's flowing, you're breathing, but there's no oxygen going around your body. So that's why we have carbon monoxide detectors in our house. That's why you should never barbecue in your house. That's why you should always have fires in well-ventilated areas, well-ventilated rooms. Go outside, have a campfire. That's the best place, because I don't want to say almost all, but I'm not going to say all, but I'm going to say almost all combustion is incomplete combustion. So you're always going to have the production of some carbon monoxide. Something that you will definitely see is carbon soot. So that is that black cloud of smoke that you see coming out of a truck that has seen better days. That is your soot. Okay, and that is a solid. I'm sorry, my house is getting louder and louder by the minute, but thankfully we're done. Okay, so that is a product of incomplete combustion. So you need to know what the products are of incomplete combustion, but you don't need to know how to balance it. Also, if you remember, whenever there's a hydrocarbon that has sulfur, or a hydrocarbon that has nitrogen in it, remember, we're burning fossil fuels. These were living organisms, mostly plants, from millions of years ago. We are not just made up of carbon and hydrogen. Life is not made up of just carbon, hydrogen, oxygen. There's also sulfur, nitrogen, phosphorus, and lots of other things. So the sulfur that is found in hydrocarbons when it is burned, it forms sulfur trioxides or sulfur dioxides, which then in the atmosphere combines with water, and guess what you get? Sulfuric acid and sulfurous acid. Now I'm simplifying this a lot, okay? And then with the nitrogens, you get nitrogen monoxides and nitrogen dioxides, which again, when you put it into the atmosphere, when you combine it with clouds, you're going to get you're going to get nitric acid, okay, or nitrous acid. This is both the cause of acid rain, right? So that's why it's much better to have clean, refined fuel. All right, we got through it, woohoo. Hopefully you made it through this full video. What are we going to do with this? I'm not too sure. We do want to have some sort of quiz, some sort of assignment. So this will help you get through the quiz and assignment. If you have any questions, let me know. That we are done Unit 2. We are going to start Unit 3 on Monday. All right, take care, you guys. Get outside. It's beautiful.